Sky metal, rarer gold, ancient secret, ashes talk, fire reveals. Ancient Egyptians prized iron more than gold, found inside meteorites. Tutankhamun's dagger was forged from metal that fell from space. Iron existed for centuries before humans learned to smelt it themselves. Ordinary campfires accidentally reached temperatures hot enough to extract iron. Bog iron, hidden in swamps, became humanity's first true iron source. Blacksmiths discovered steel by accident, without knowing any real chemistry. The Hittites guarded iron smelting as a closely protected royal secret. One empire's collapse accidentally spread iron technology across the ancient world. Iron farming tools quietly transformed food production for entire civilizations. Iron weapons ended Bronze Age warfare almost overnight, changing history forever. Quenching hot iron in water created stronger blades through pure trial. Wood steel from India became legendary, called the finest blade metal. Damascus swords held secrets modern scientists only recently began understanding. Charcoal, not fire alone, was the true key to smelting iron. Slag removal separated pure iron from rock through repeated hammering. Carbon atoms trapped inside iron secretly created the first steel. This video reveals exactly how rocks became civilization's most powerful tool. You'll see meteorites, furnaces, blacksmiths, empires, and one incredible chemical accident. Every step happened without anyone understanding atoms, elements, or chemical bonds. By the end, you'll understand chemistry ancient humans discovered through instinct. This isn't a lecture, it's the real investigation behind iron's discovery. Stick around, because the final reveal changes how you see history. Nothing here is generic. Every fact is pulled from real archaeological research. This story built empires, ended wars, and shaped the modern world. Let's go back to the moment fire first met iron ore. Long before mining existed, humans found iron falling from the sky. Meteorites contain natural iron-nickel alloys already usable without smelting at all. Ancient people called meteoric iron metal of heaven in several languages. Egyptian hieroglyphs literally translate iron as bizenpet, meaning heavenly metal. Tutankhamun's tomb held an iron dagger forged from a meteorite, confirmed scientifically. Researchers used X-ray analysis to detect meteorite-level nickel inside that blade. Meteoric iron naturally contains nickel percentages, no earthly ore matches easily. That nickel signature lets scientists trace ancient iron back to space. Sumerians also referenced iron using symbols connected directly to the sky. Before 1200 BCE, iron artifacts were incredibly rare and highly valuable. Iron cost more than gold because meteorites were scarce and unpredictable. Kings exchanged iron objects as prestigious gifts between powerful royal courts. A Hittite king once refused to send iron, calling supplies limited. That letter proves iron was treated as a precious royal resource. Meteoric iron could be hammered cold without needing intense smelting heat. This made it usable long before humans understood furnace-based extraction. Early blacksmiths shaped meteoric iron using stone tools and pure force. Some ancient beads were hammered from meteorite fragments thousands of years ago. Archaeologists found meteoritic iron beads in Egypt dating back 5,000 years. These beads predate organized iron smelting by roughly 2,000 years. This discovery pushed back humanity's iron timeline earlier than previously believed. Iron from space quietly primed humans to recognize iron's real potential. People noticed this heaven metal was tougher than bronze weapons available then. Yet meteorites were random, rare, and impossible to intentionally collect reliably. Humanity needed another method, since space couldn't supply enough iron. The real breakthrough required extracting iron directly from ordinary earthly rock. That leap demanded accidental chemistry, centuries before atoms were ever understood. Ironically, fire itself would become the unexpected teacher of chemistry. Certain rocks, called iron ore, silently held metal trapped inside them. Iron ore looks unremarkable, easily mistaken for regular reddish-colored stone. Hidden inside that stone sits iron bonded tightly with oxygen atoms. Breaking that bond required heat far beyond typical open campfires. Early humans had no idea chemical reduction reactions were even happening. Yet repeated fire use eventually created exactly the right hot conditions. Pottery kilns, already common, accidentally reached temperatures near iron's melting threshold. Potters likely noticed strange metallic lumps appearing inside failed clay firings. This accidental byproduct may have sparked humanity's very first curiosity. Nobody planned iron smelting. Chemistry essentially discovered itself through repetition. Trial, error, and countless failed fires slowly revealed a working pattern. Certain ores, combined with charcoal, produced small workable iron blooms. These crude iron lumps looked unimpressive, yet marked a massive breakthrough. This transition moved humanity from scavenging space metal to producing iron. From here, deliberate experimentation with furnaces and heat truly began. Humans were no longer waiting on rare meteorites falling from space. They were actively pulling iron directly from the ground itself. This shift changed everything about how civilizations would build their future. Iron stopped being mythical and slowly became an achievable earthly resource. What followed next would trigger one of history's greatest technological revolutions. The next question was simple: how hot does fire really need to get? That single question led directly into the invention of the furnace. Extracting iron from ore demanded far more heat than open fires gave. Ordinary campfires reach around 700 degrees Celsius at best. Iron ore needs roughly 1200 degrees to properly release metal. Ancient humans solved this gap using clever pit and furnace design. Early furnaces, called bloomeries, were simple clay-lined pits or chimneys. Charcoal, not raw wood, provided the higher sustained heat required. Charcoal burns hotter because impurities and moisture are already removed. Layering ore and charcoal together created the right chemical conditions. Airflow mattered enormously, since oxygen fuels combustion inside the furnace. Ancient smiths used bellows, manually pumping air into the fire. This constant airflow pushed furnace temperatures high enough to reduce ore. Inside the furnace, carbon monoxide gas quietly performed the real chemistry. Carbon monoxide pulled oxygen away from iron atoms inside the ore. This reaction, called reduction, is basic chemistry ancient humans never studied. They just knew charcoal and airflow together produced usable metal. The result wasn't liquid iron but a spongy solid called bloom. Bloomery furnaces couldn't reach iron's true melting point of iron itself. Instead, iron formed as a soft, impure semi-solid clump. This bloom contained iron mixed heavily with rock and slag waste. Blacksmiths then repeatedly hammered the bloom to squeeze slag out. Hammering while hot forced impurities out, consolidating iron into workable metal. This process, called forging, demanded serious physical strength and patience. Early iron working was exhausting, dangerous, and required specialized furnace knowledge. Communities that mastered this process gained enormous technological advantages instantly. The Hittite civilization is widely credited with early organized iron smelting. Around 1200 BCE, Hittites controlled valuable ironworking knowledge and techniques. They treated iron smelting almost like a closely guarded state secret. Iron tools slowly began outperforming existing bronze equivalents in strength. Yet early bloomery iron wasn't automatically better than well-made bronze. Raw bloomery iron was actually softer than properly alloyed bronze weapons. The real advantage was iron ore's abundance compared to scarce bronze materials. Bronze required tin, a rare resource controlled by limited trade routes. Iron ore, meanwhile, existed almost everywhere across various ancient landscapes. This availability meant iron could eventually be produced on massive scales. Widespread iron access slowly outweighed bronze's early performance advantages entirely. Around 1200 BCE, major Bronze Age civilizations suddenly collapsed dramatically. Trade routes supplying tin for bronze production were violently disrupted. This crisis forced societies to search for accessible metal alternatives quickly. Iron, already locally available, became the practical emergency replacement metal. This historical turning point is now called the beginning of Iron Age. Ironworking knowledge spread rapidly once Hittite secrecy eventually broke down. Migrating peoples and displaced smiths carried furnace techniques across regions. Within centuries, iron smelting appeared independently across Europe, Africa, and Asia. Different cultures adapted furnace designs based on local available materials. African bloomery furnaces, for example, achieved impressively high smelting temperatures early. Meru, in ancient Sudan, became a major regional iron production center. Iron production there rivaled techniques found across parts of ancient Europe. This proves iron chemistry was independently mastered across multiple civilizations. Humans everywhere solved similar chemical puzzles using local trial and error. But raw bloomery iron still had one major remaining weakness left. Bloomery iron, while useful, remained relatively soft compared to modern expectations. Blacksmiths noticed something strange happening during repeated prolonged charcoal fire exposure. Iron left inside hot charcoal fires slowly absorbed trace carbon atoms. This process, called carburization, accidentally transformed plain iron into steel. Nobody understood carbon atoms, yet the reaction happened consistently anyway. Steel formed only in iron's outer surface layers during early smelting. Repeated folding and hammering helped distribute that carbon more evenly. This explains why ancient blacksmiths folded iron dozens, even hundreds, of times. Each fold thinned carbon-rich layers, spreading strength throughout entire blades. Folding also removed remaining slag, improving overall blade purity significantly. Blacksmiths discovered quenching almost entirely through dangerous physical experimentation. Plunging red-hot iron into water rapidly changed its internal structure. Quenching locks carbon atoms into a hard, brittle crystal structure. This structure, now called martensite, dramatically increases overall blade hardness. However, quenched steel alone often became dangerously brittle and prone to cracking. Ancient smiths solved this by reheating blades slightly after quenching them. This secondary process, tempering, reduced brittleness while retaining useful hardness. Tempering releases some internal stress, creating a tougher, more flexible blade. None of these smiths understood crystal lattice or atomic bonding structures. They simply observed results and repeated whatever techniques consistently worked well. This trial-based knowledge passed down secretly through generations of blacksmiths. India developed one of history's most legendary steelmaking traditions early. Wootz steel, produced in southern India, became famous across ancient trade routes. Crucible, steelmaking, sealed iron, carbon, and glass inside sealed clay containers. This crucible method allowed extremely controlled, slow carbon absorption processes. Wootz steel produced distinctive wavy patterns, prized by weapon makers everywhere. Middle Eastern smiths later forged this imported steel into Damascus blades. Damascus swords became legendary for exceptional sharpness and remarkable flexibility. Historical accounts describe Damascus blades slicing through silk scarves midair. Modern scientists eventually studied Damascus steel using powerful electron microscopes. Researchers discovered carbon nanotubes embedded naturally within Damascus steel samples. These nanotubes likely formed accidentally through specific ancient smelting conditions. No blacksmith ever intended or understood creating nanoscale carbon structures. Pure accident and centuries of refinement produced nanotechnology before science existed. This discovery amazed modern metallurgists studying ancient manufacturing techniques closely. It proves ancient experimentation sometimes outperformed early scientific theoretical understanding. Eventually, original Wootz steel production techniques mysteriously disappeared entirely. Historians believe specific regional or compositions were essential, then lost. Without that particular or replicating true Wootz steel became impossible. This mystery remained unsolved for centuries after production eventually stopped. Meanwhile, steelmaking knowledge continued advancing independently across other world regions. China developed early cast iron techniques significantly earlier than Europe did. Chinese furnaces reached higher temperatures, enabling true liquid iron production earlier. This allowed casting complex iron shapes directly using reusable molds. European blacksmiths remained limited to bloomery methods for much longer periods. Different regions solved identical chemical problems using completely different approaches. Steel eventually became the defining material separating advanced ancient civilizations. Stronger tools meant better farming, construction, and eventually devastating warfare capability. Steel weapons transformed battles, giving decisive advantages to prepared civilizations. But steel's true impact reached far beyond simply swords and warfare. Iron's real revolution happened quietly, inside ordinary farming fields everywhere. Iron plows cut through dense soil far better than fragile bronze. This allowed farmers to cultivate previously unusable, harder agricultural land. More farmland meant significantly larger, more reliable food production output. Larger food supplies directly supported rapidly growing ancient populations everywhere. Population growth allowed cities to expand well beyond previous limitations. Iron axes also made forest clearing dramatically faster and more efficient. This opened previously inaccessible regions for permanent human settlement expansion. Iron nails and tools improved construction techniques across many civilizations. Buildings, wagons, and infrastructure became stronger and considerably longer lasting. Iron horseshoes eventually improved transportation speed and overall trade efficiency. Better transportation connected distant regions through expanding ancient trade networks. Militarily, iron weapons were significantly cheaper to mass produce than bronze. Entire armies could now be equipped without expensive imported tin supplies. This allowed larger, better equipped forces previously impossible under bronze economies. Assyrian empires aggressively expanded using iron weapons and iron-based tactics. Their armies gained major advantages through widespread iron weapon standardization. Iron chariots, armor, and tools strengthened Assyrian military dominance significantly. Roman civilization later perfected iron production at truly massive scale. Roman iron mines and furnaces operated across vast conquered territories. This industrial-level iron production helped sustain Rome's expanding empire. Roman roads, tools, and weapons relied heavily on consistent iron supply. Meanwhile, African kingdoms independently built sophisticated iron production economies too. The Kingdom of Meru exported iron tools across surrounding regions. Iron smelting became a major economic and cultural cornerstone there. In East Asia, Chinese dynasties used advanced iron casting for governance tools. Iron currency tools and weapons supported large, centralized administrative systems. Iron effectively became a universal marker, separating advancing ancient civilizations. Societies without reliable iron access often fell behind economically and militarily. This created significant global technological gaps between different ancient regions. Trade routes formed specifically around valuable iron ore and finished tools. Control over iron resources sometimes determined regional political power balances. Wars were fought partly over access to valuable iron-producing territories. Blacksmiths themselves gained significant social status within many ancient communities. Their specialized knowledge made them essential, sometimes almost mystical, figures. Some cultures associated blacksmiths with magic, given their transformative fire mastery. This respect reflected iron's genuinely transformative impact on daily survival. Iron tools improved hunting, cooking, farming, and basic household efficiency. Everyday life gradually became easier through widespread iron tool availability. Iron eventually replaced stone, bronze, and wood across countless daily tools. This transition took centuries, spreading unevenly across different world regions. Yet the long-term trajectory remained consistent. iron dominance kept increasing. By classical antiquity, iron had become civilization's essential foundational material. Empires rose and fell, but iron dependency only continued strengthening. This dependency eventually paved the way toward future industrial revolutions. Centuries later, iron and steel would fuel entirely new technological eras. Railroads, machinery, and modern infrastructure all trace back to iron. Everything started with ancient humans accidentally heating rocks over fire. No chemistry textbooks existed, yet real chemical revolutions kept happening anyway. That accidental science quietly built the foundation of the modern world. Iron's story began accidentally, inside campfires nobody expected to matter. Meteorites first revealed iron's potential, long before smelting ever existed. Ordinary rocks secretly held metal, waiting centuries for accidental discovery. Charcoal, airflow, and countless failed attempts unlocked real furnace chemistry. Bloomery furnaces transformed rock into humanity's most transformative material ever. Blacksmiths accidentally invented steel while simply trying to strengthen iron. Quenching and tempering emerged through dangerous, repeated physical experimentation alone. Wootz, steel, and Damascus blades hid nanoscale secrets nobody understood. Modern science only recently explained what ancient smiths achieved instinctively. Iron transformed farming, construction, transportation, and everyday human survival completely. It reshaped militaries, economies, and entire ancient civilizations permanently. Empires rose specifically because they mastered accessible, abundant iron resources. Societies without iron access often struggled to compete effectively. This wasn't planned science. It was chemistry discovered through pure necessity. Every furnace, every hammer strike, quietly advanced human technological understanding. Nobody involved understood atoms, elements, or chemical bonding whatsoever. Yet their discoveries mirror principles modern chemistry still teaches today. Ancient humans essentially performed real chemistry without ever naming it. That's what makes this story genuinely remarkable and worth remembering. Iron didn't just build tools, it quietly built entire civilizations. This accidental chemical revolution still shapes technology surrounding us today. Every steel building and railroad traces back to that first furnace. Ancient blacksmiths were, without realizing it, humanity's earliest chemists. Their fire-based experiments quietly laid groundwork for future scientific discovery. Understanding this history reveals chemistry's roots long before laboratories existed. Real breakthroughs often come from curiosity, patience, and repeated experimentation. Iron's journey proves discovery doesn't always require formal scientific understanding. If this story fascinated you, chemistry's history holds countless more surprises. Subscribe for more deep dives into science hidden throughout human history. Let me know which ancient discovery you want explored next.